All right. Hello, everyone. Thanks for joining us today, and welcome to today's section of the GLASE Webinar Series entitled Strawberry and Tomato Responses to Light and CO2 Control. My name is Erico Mattos. I'm the director of the GLASE Consortium, and I will be your host today. The GLASE Consortium Webinar Series is a selection of live recorded online presentations that cover a broad range of topics at varying technical levels and scale. These webinars feature the latest technological innovations and best practices in the CEA field, providing the audience the opportunity to discover new solutions and to connect with field experts. I would like to introduce today's presenters, Dr. Neil Madsen and Jonathan Allred from Cornell University. Dr. Neil Madsen is an associate professor in the School of Integrative Plant Science, having joined Cornell University in 2007. He serves as the statewide greenhouse specialist here in New York, with research and outreach programs focusing on physiology of both vegetable and flower crops. His work emphasizes strategies to optimize crop production while reducing energy use to improve lighting in greenhouse control systems, plant mineral nutrition, and plant stress physiology. Neil is also the lead researcher at the GLASE Consortium at Cornell University. Presenting with Neil today, we have Jonathan Allred, who is a PhD student at Cornell University. Jonathan received his BS in plant science at Cal Poly Pomona with focus on field crops. In 2015, Jonathan joined the Madsen lab at Cornell, where he obtained his MS in horticultural biology with focus in controlled environmental agriculture, biological and environmental engineering, and economics as they relate to microgreens cultivation. In 2017, Jonathan accepted the position as a PhD student at Cornell, remaining in the Madsen lab. Currently, Jonathan focuses on optimization of day-neutral strawberry cultivars in controlled environments through the modification of various environmental parameters. I would like to remind you that a recorded version of this webinar will be available at our website, glase.org, afterwards. If you have any questions about the presentation, or if you'd like to get in contact with the speakers, please submit your inquiries using the chat box. So you see a chat box, there's a Q&A section. You can let us know if you have any questions, and we're going to do our best to answer all those questions at the end of the presentation. But you can submit the questions during the presentation. We're going to read them at the end of the presentation. So now, with no further ado, I would like to pass the word to Neil and Jonathan. And just before we start, I'm going to launch two polls here to take a look on who are our audience. So that'll be great for Jonathan and Neil, and as we conduct the presentation.
Great. Thank you, Erico. So you'll start the poll.
Perfect.
And good.
Yeah, graphics. So seeing who's the audience, Neil.
Perfect. So which category do you belong to? Greenhouse growers, indoor growers, lighting manufacturers, service providers, retail, academic or research, or other? Okay, and are you getting some responses, Erico?
Yes, 80% right now has voted.
Okay.
Just a few more seconds, we can take a look at the final results. Almost there. Let's go, folks. We need.
They must be heating up their lunch or grabbing a cup of coffee.
Exactly. All right, that's about a minute. So let's take a look here. Share results. So we have the majority of the attendants today are lighting manufacturers, 22%. Then we have academic and researchers. We do have a good amount of growers, 18% greenhouse growers, 16% indoor growers, and we have 18% on other categories. Perfect. Let me see the second question here. We have another one. Which for some reason don't want to come to me.
I see your first question.
Yeah. Okay, found it here. Okay, so lunch poll. Perfect. So the second question, if you are a CEA grower, which crop do you grow? So you can take a look on the crops being cultivated out there.
Okay, as the panelists vote, or the attendees vote, we'll
All
see
the
what they
attendees
say.
involved. Yeah.
Okay.
So far, leafy greens is heading. Greens is the yeah, leafy greens, microgreens so far. Come on, everyone. 10 more seconds. All right. So sharing the poll results, majority of the growers today are leafy greens growers, 66% of the audience. And that's one is multiple, we can choose multiple options. So we have leafy greens, microgreens, the second one with 51%. Then we have vine crops, 32%, cannabis 27%, and hemp 20%. Other 37% of the audience.
Very good.
All right, perfect. Neil, the word with you now.
Great, I'll take it away. So the way that we have things set up is I'll talk for about 20 minutes on more of the basics of carbon dioxide supplementation, some of the typical crop responses, so what you can expect in terms of yield, a bit more on specifically delivery methods and control methods for using CO2 in your operation. And then I'll introduce a bit of our own GLASE research with light and carbon dioxide control. And then at that point, we'll switch over to PhD student Jonathan Allred, who will spend about 20 minutes talking about his work with greenhouse strawberries and cultivar studies, so selecting for high yielding, high performing cultivars, and then strawberry responses to supplemental light. And the reason why we're interested in carbon dioxide as plant scientists is because it's a reagent in photosynthesis. So if you all remember your high school biology class, right, CO2 combines with water to give us sugars. And so when the crop is lit and actually performing photosynthesis, that's when we would add carbon dioxide. And commercially, we often add it to about 700 to 1200 parts per million. We'll give some examples later on that we'll talk about what might be the rate to choose for your crop. Above about 1,000 parts per million, we tend to see these declining returns. And the response of CO2, and we'll show some examples for greenhouse crops. This one was a nice one from the literature from eucalyptus, so a plant in nature. But in this work, they used a photosynthesis machine to give the plant light from 0 all the way up to 2,000 micromoles per meter squared per second, where 2,000 would be full sun on a summer day. And then they measured the rate of photosynthesis at 3 different carbon dioxide levels. So currently we get about 400 parts per million. So that would be close to the middle line. That's what we naturally have outside. And we often supplement to about 1,000 parts per million. And so what you can see, for example, at say 500 micromoles per meter squared per second of light is if we have close to ambient CO2, so our middle line, and then we add 1,000 parts per million CO2 without adding additional light, we are seeing in this case about a 30% increase in photosynthesis. And at higher light levels, there were even greater effects on CO2. From a human perspective, the levels of CO2 that we use in a greenhouse operation are fine. When we start getting into concentrations above 5,000 parts per million, that can lead to dizziness. And actually OSHA requires that CO2 for workers be less than 5,000 parts per million during an 8-hour workday. So we shouldn't approach these levels, but if something does go wrong in an operation, it would be best to have a CO2 alarm sensor just to verify that. And one of the uses for CO2 is also just to use in the wintertime to replace what's being taken up by the plants. And so in this case, let's say we have a well-sealed greenhouse, maybe it's a double poly greenhouse with very few cracks and leaks, which is really great in terms of saving on heat and an energy perspective. But what will happen is the plants will draw down the carbon dioxide that's in the greenhouse. So we require actually a bit of ventilation to replace the CO2 that the crop is absorbing while it's photosynthesizing on, say, a sunny, cold winter day. And there was some work done at the USDA ARS in Toledo, Ohio, where they found that poor ventilation in a greenhouse in the wintertime, you could get carbon dioxide to drop to, say, 340 parts per million under conditions of medium light or a medium-sized plant, so a decent-sized canopy in a greenhouse. And if you had high light or a large plant canopy, I think of like a large stand of tomato crops with good leaf area index, that CO2 could go down to 310 parts per million. And in the work at the USDA ARS in Toledo, they found that financially it was cheaper to add CO2 instead of ventilating the greenhouse and then having to reheat that air. So one use of CO2 is just to make sure that CO2 is always at ambient levels at about 400 parts per million. In terms of some of the different crops that we grow in the greenhouse, here are some example reported yield increases. So with tomatoes, if we add to 1,000 parts per million, often yield increases of 30 to 38% are seen. Cucumbers, even just supplementing to 620 parts per million, there's reports of 34% yield increases. Peppers, only to 450 to 500 parts per million CO2, there would be yield increases of 15%, and lettuce up to 1,000 parts per million, some yield increases of 25 to 40%. If you're adding carbon dioxide to your CEA environment, there's a couple different ways that you can do this, and we'll broadly classify these as byproducts of combustion or as using CO2 from a liquid tank. And so in terms of using it from a byproduct of combustion, you might use a boiler. So if you have a central heat source in a greenhouse, you can capture the exhaust from the boiler, which will naturally be high in carbon dioxide. Typically that would go through some type of kind of like catalytic converter to scrub off gases, and then that would be pumped into the greenhouse. This is often used in combination with hot water storage. And so what we think about is your plants need the carbon dioxide during the day or when the lights are on in the greenhouse, but that might not be when you need the heat in the greenhouse. So if you have a really large hot water storage tank, you can still run your boiler during the daytime to use the CO2 from the exhaust, and then you will have that stored hot water that you'll use for heating your greenhouse during the nighttime. The other way that the combustion CO2 can be used is from burners. So often like a natural gas burner, which would be an unvented burner in a greenhouse. And we see two examples of that in the photos on the right here. One thing that one has to think about using that approach is the burner has to be adjusted so that you have a clean burning flame. And so if the flame should be, blue instead of orange or yellow, and if it is not burning properly, there can be undesirable off gases such as carbon monoxide, ethylene, or nitric oxide. Ethylene and nitric oxide we're worried about from a plant health perspective, and they can cause undesirable effects on the plant. The other source of CO2 is from a gas supply company, and this would be harvested as a byproduct from industrial processes. And so this would be a purified CO2 source that can either be compressed air or more commonly liquid. So the liquid will take up less space, but it will require a tank with refrigeration. When you're using this purchased CO2, then we're not worried about potential off gases like ethylene and nitric oxide. I have seen several operations that will use a hybrid approach. So when they are operating their boiler very intensely in the wintertime to keep their operation heated, they'll use CO2 from their exhaust. And then in the summertime, when they still want to see the benefits of CO2, but they're not operating their boiler very much, they'll use liquid CO2. And a typical control strategy for when you add CO2 into a greenhouse takes into account whether you're ventilating your greenhouse. So if you're ventilating your greenhouse and it's a warm, sunny day, the CO2 that you add is going to be rapidly lost from the greenhouse and won't really get to your crop and be helpful. So in this typical control strategy, one looks at whether you're heating a greenhouse, yes or no, and then whether you're ventilating. And so if you're heating your greenhouse and not ventilating it, that would be a good time to add as much CO2 as possible, at least to where you see a beneficial crop response. So maybe that's when you're adding up to 1,000 parts per million CO2. When your ventilation is occurring but limited, so CO2 that you add will be lost over time. You will add a low amount of CO2. Here we're trying to reach maybe just ambient CO2. And then when your ventilation is increasing, we will throttle down our CO2 addition. So at this point, it's not making sense to add additional CO2. And when your ventilation is running on high, we're not adding any additional CO2. We're just getting the ambient CO2 that's outside. When we distribute CO2 into a greenhouse, what's often used are these small polyethylene tubes with holes punched in them across. And so in the case of this tomato canopy, for example, running this tube across through the canopy across the row will distribute CO2 directly into the plant canopy where the leaves can actually access it and use it for increased photosynthesis. Just as an example of if you're paying to add CO2 from like a liquid tank, for example, there are some rough calculations that you can do. You can also work with your gas supplier to do more specific calculations for your operation and based on their experience. But this was just one example where we're considering, you could consider a couple different scenarios. One scenario is just maintaining CO2 at 400 parts per million. And the mantra that we kind of follow in the northern half of the US is we use about 50 kilograms of CO2 per hectare per hour, which if you use the English unit system is 45 pounds per acre per hour. If we actually want to elevate CO2 to achieve something closer to say 1,000 parts per million CO2, and this is still assuming low ventilation rates during this time, we'll be adding about 180 pounds per acre per hour. So then if we know the cost per CO2, kind of a common cost currently is 50 cents per kilogram or 23 cents per pound. And then we have some estimate of the hours of enrichment that we're doing per year. So if we think of a scenario where we're not enriching during the summertime because we're ventilating a lot, we're targeting our enrichment during lit hours in the wintertime. So we could think of using it for 125 days per year at 8 hours per day would give us 1,000 hours per year. And so if we then do that math at 180 pounds per acre per hour times 1 acre times 1,000 hours per year, we end up with using, I have to drag this bar away. We end up using 23 times 23 cents per pound. We end up costing $41,400 per year. To put that in comparison, if I was adding supplemental light to a 1 acre greenhouse using high pressure sodium lights and to a 200 micromoles per meter squared per second target, with my electricity costing 10.5 cents per kilowatt hour, that light is costing me about $120,000 per year. And with LEDs, maybe we'd be looking at $80,000 per year just for the electrical cost. So it can be substantially cheaper than lighting, and it can really reduce our need for adding supplemental light. Some examples of crop responses to CO2. So with lettuce, there's been quite a bit of work previously with leafy greens, some of it here at Cornell University back in the mid-1990s. And there was some work where there were different combinations of daily light integral and CO2 that were chosen. So the daily light integral from 11 all the way up to 16 moles per meter squared per day, and then CO2 was kind of selected to complement that. So we had the highest CO2 at 1,500 parts per million CO2, and then that went down to 400 parts per million CO2. What was found in this work is that all of these combinations produced a nice head of lettuce, so 190 gram fresh weight head of lettuce, or about 6 ounce head of lettuce. And so if we could use only 11 moles of light, that could really reduce our need for supplemental lighting. What was found in this particular project in this greenhouse is that the 2 highest CO2 concentrations could not be easily maintained in these somewhat leaky greenhouses, and also due to ventilation. So from a practical standpoint, if we could add 1,000 parts per million CO2, we could get away with using about 30% less light, so having about 13 moles of light instead of 16 moles of light. We have a PhD student at Cornell that's recently been working on lettuce responses to CO2. And here's some work for this red leaf cultivar that's called Brix. And he did these short-term experiments where he would expose young heads of Brix to carbon dioxide for several days, and then look at the plant fresh weight. And so at ambient CO2, these young plants averaged about 30 grams per head with ambient CO2. And then if we went up to about 1,200 parts per million, we could get a head that was 42 grams. So under the same lighting conditions, but just with more CO2, we got about a 30% larger head of lettuce. And here's photos from what those plants look like. So again, you can see under the 1,200 and 1,600 parts per million CO2, there was a decently larger head of lettuce. We'll have Jonathan shortly be talking about strawberry responses to light. Jonathan also did a nice work looking at instantaneous responses in terms of photosynthesis, kind of like that graph that I showed for eucalyptus at the beginning of the talk. And so he would use this, this expensive piece of equipment, this photosynthesis machine. We have an example here where it's getting clamped onto a tomato leaf, but this is work done with the strawberry cultivar Cabrillo. And what we can learn quite a few things from a graph like this. So if we look at our x-axis, again, this is light levels increasing from 0 up to 2,000 micromoles per meter squared per second. And then the y-axis is our net photosynthesis rate. So for ambient CO2 would be the blue line, so 400 parts per million CO2, and then 675 is red, and 950 is green, and purple is 1225. And so if we look at, say, 500 micromoles of light, there was a large bump in photosynthesis when we increased CO2 just to 675 parts per million. There was a slight bump increasing it to 950. So this would suggest you could still see some photosynthetic increase with increasing it to 950. And then for strawberries under these conditions, there didn't seem to be much benefit of increasing CO2 further to 1,225 parts per million. So that photosynthesis data is great, but we still have questions about how the plants will respond in terms of their fruiting and their yield response. So this winter, a grad student, Masaki Kirosaki, is going to be growing tomatoes, and Jonathan's going to be growing strawberries. And we have an experiment set up that will be running 2 different daily light integrals, so 10 moles per meter squared per day, and then 20 moles per meter squared per day. So kind of our higher light, which should be more common for tomatoes and strawberry minimum lighting in the wintertime. And then for each of those, we'll have close to ambient CO2 at 450 parts per million, and then we'll supplement that to 1,000 parts per million CO2. So we look forward to seeing those results. In terms of CO2 and light control, we're also doing some work under the GLASE project on kind of more sophisticated control strategies. And so we have one that's related to just controlling the daily light integral in a greenhouse. And then we'll talk about merging that with CO2. So with controlling light, Lou Albright, our retired professor at Cornell, developed this light and shade system implementation control or algorithm. We like to call it Lassi, so that's why we have the picture of the dog here. And what it will do is it will take, typically we have highly variable daily light integral in our northern climate in New York. This is an example from 1 year in upstate New York, and each dot is the daily light integral for 1 day out of the year. And so this algorithm adjusts the supplemental lights in a greenhouse as well as the shade curtains to achieve a stable daily light integral. So we reach our lighting target using lighting if we need to, and then we can shade the sun if we need to avoid the plant getting too much light. And this algorithm actually predicts natural light accumulation based on the time of the year and your location and the first few hours after sunrise. And so it uses this predictive approach to decide when lights need to be turned on instead of using a light threshold approach. This algorithm can also be set up to schedule supplemental lighting during the nighttime if you have an off-peak electrical rate structure. And Cale Harbeck and our group at Cornell has looked at the electricity savings potential of using a Lassi control algorithm versus what's most common in greenhouses, just using an instantaneous light threshold. In that strategy where light goes below a certain threshold level, that's when it would trigger supplemental lights turning on. And then when light goes above a threshold, those supplemental lights will turn off. But this more predictive control avoids some of those kind of overshading and then having to overlight to make up for that. And so in a northern climate where we use a fair bit of supplemental light in like Elmira, New York or Helena, Montana, we can save 20 to 30% of our electricity using this more predictive approach. And the reason for that, so if we look at these two control strategies, here we have example data with the threshold control is the graph here on the left, and these dots are the daily light integral for a day. And then inside a greenhouse that's running this lighting, this Lassi control algorithm, we very closely hit the 17 mole target. So the threshold control has more aggressive shading, and the user could kind of fine tune that, but it tends to shade more than it should, and it does not anticipate the sunlight that could accumulate for the rest of the day. And so because of that, then one needs to use greater supplemental lighting at the end of the day to hit your DLI target. With this threshold control, as you can see, these dots are much more scattered around that 17 mole target. And so there's many days where daily light integrals are either above or below that target. So we also have a version of Lassi, also developed by Dr. Albright, that takes into account carbon dioxide supplementation. And in this strategy, what we do is we try to reduce the need for adding supplemental light if we can enrich with CO2. So in the case of like lettuce, for example, it's kind of taking that scenario of 16 moles of light at ambient CO2 is the same as 13 moles of light with 1,000 parts per million CO2. And in this control algorithm, it determines the optimal level of CO2 and lighting to reduce the total cost of reaching that virtual daily light integral for the rest of the day. It does this in the original algorithm on an hourly by hourly time step. It assumes that if you need to, you could just use lighting to reach your target for the rest of the day, so that no matter what happens in terms of ventilation in the greenhouse and our ability to add CO2, we know that we could at least use the lights to hit our DLI target. To determine the rate of carbon dioxide loss, this algorithm needs to know the ventilation rate in a greenhouse that's being used for temperature control. And then it also accounts for the cost of the amount of CO2 it would have to use in an hour based on that ventilation rate. So then the algorithm can decide, is it going to be cheaper to add more supplemental light or cheaper to add more CO2 to reach the same virtual daily light integral. And we've run some scenarios. This is a researcher at Cornell, Tim Shelford, who's done this work where we looked at the standard Lassi, and with an installed lighting capacity of either 180 or 250 micromoles per meter squared per second. And what he's trying to look at there is, if you paid to install a greater lighting capacity, then you could put more of your supplemental lighting to take place during the off-peak hours of the day when electricity is cheaper, but you do have a higher upfront cost with your lighting. In these calculations, using Lassi to achieve our daily light integral targets would cost us either $28 or $18 and per meter squared per year. And then there was substantial savings if we could use CO2 Lassi. So if we can use CO2 enrichment where appropriate, we could save about 36% of our lighting costs if we had an installed light level of 180 micromoles. And we'd save a bit less, we'd save about 18% if we had that higher installed lighting capacity. And this scenario did account for the cost of adding CO2 at 50 cents per kilogram. So with the GLASE project, we're working on installing the CO2 Lassi algorithm first in our greenhouse on campus and then in a couple different commercial pilots in New York to try it out at a commercial scale. Okay, this is my slide. That is my segue between myself and Jonathan. So I'll welcome grad student Jonathan Allred to the webinar.
All right. Hello, everybody. I am going to take over at this point. I have a little bit of extra material to cover. We're going to try and go through this as quickly and proficiently as possible. So when we first started the research here at Cornell, strawberries were new for us, and strawberries in the United States in greenhouse production is a relatively juvenile industry. So the first question that we needed to answer was the different cultivars that we were going to use to do the experiments with and determine how appropriate they are for production in controlled environments. And so looking through existing research that was out there, as well as determining the sources of available materials, we decided to pull most of that material from the University of Davis, California breeding program. And so with the exception of one of these cultivars, which is Sweet Anne, the Albion, Cabrillo, Seascape, Portola, and San Andreas all came from the University of Davis. Now, each of these individual cultivars have their own characteristics. These characteristics are predetermined and defined by the university as well as different propagation companies. But some of the general attributes are, for Albion, it has a nice firm berry, a medium-sized fruit, flavorful, and medium aroma. Cabrillo is a moderately firm. It's a little bit softer. It's a large fruit as well. It's mild flavor and lower aroma. Seascape is a classic variety that's been grown for many years. It's actually off patent. And it's a softer berry, small to medium-sized fruit, and flavorful and strong aroma. Portola, we did move forward with this in our trials. However, Portola, it has a good fruit, moderately firm, medium, large, relatively large size. However, the inflorescence structure on Portola tends to grow a little bit longer than the other cultivars, and when it bends over a pot structure in a greenhouse type environment, it will often snap under the load of the fruit. So ultimately, that'll play into some of the numbers we'll see, but ultimately that was removed. San Andreas and Sweet Anne, they were not included in this trial. San Andreas was initially removed due to some issues with viviparity, which is essentially a genetic physiological disorder where the seeds themselves start to grow on the berry. And so that was an undesirable trait. In specific greenhouse operation, it was happening quite frequently, so we removed that. It's not necessarily characteristic of San Andreas overall. And Sweet Anne was also removed. It just tended to have a higher rate of vegetative production and less inflorescence development. And so ultimately, some of the things that we're interested in was day length and sensitivity. We wanted to look specifically at day neutrals as a possibility. We wanted the plant material to be available to most growers in the United States and not have to import anything in from out of the country. We wanted medium to large berries, high vegetative, relatively higher vegetative vigor associated with them. And we wanted, especially for reproduction of those berries, vegetative reproduction of the strawberries in-house so we can continue replication in-house products. We wanted a relatively firm berry for shippability and transport to local markets and a strong flavor profile. So the initial cultivar screening, we had continuous production for about 6 months, from December 2017 to May 2018 under HPS lighting. This was DLI controlled using Lassi, as Neil had mentioned previously in the slides. The target DLI was about 17 moles per square meter per day of photosynthetically active radiation, and we had a temperature differential of 21 degrees C during the day and 17 at night. And so when we look at these two charts down here, the tables, we can see Albion had the lowest yields, followed by Portola, Seascape, and Cabrillo. And one of the key factors about Albion, and this comes to the sensitivity of these crops, is that upon delivery of this material, this was coming out of field production, going into the greenhouse. The storage time that Albion was held, the storage conditions that it was held under, actually imparted a significant effect on it in the greenhouse, and it had a much more delayed response to the treatments in the greenhouse and flowering and fruiting. Portola and Seascape had good yields, and Cabrillo had the highest yields. However, if we look at the fresh weight per meter squared, we can see that it's following roughly the same trends for Albion, Portola, and Cabrillo, but Seascape is much lower, and that's simply because Cabrillo, as I had shown in the previous slide, has a much smaller berry. So to put that into perspective, for this trial, the average berry weight for Albion was 11.6 grams, Portola was 11.2 grams, Cabrillo was 11 grams, and Seascape was 7.6 grams. So it was a much smaller berry and would be considered less marketable to much of the industry. When we looked at Brix, so kind of as a proxy for sugar content, we see a relatively consistent result across the different months and between these cultivars. So the highest obtainable Brix value was 10% for Albion and Seascape, and the lowest was about 8.7% for Portola. Now, this doesn't speak necessarily to Portola as having a low sugar content. It's simply because that inflorescence structure had that tendency of breaking early on, and so it didn't allow the fruit to completely mature on the flower structure. So that resulted in a lower sugar content and less ripe fruit. Moving forward, after we initially determined which cultivars seemed to have different characteristics that were desirable in the greenhouse environment, we wanted to know, generally, do day neutral strawberries need off-season or supplemental lighting in central New York to actually be produced effectively? Does that supplemental lighting source play a role? And does the month of the year play a role as well? And so when we looked at these different questions, we wanted to observe the marketable yield, marketable berry size, marketable berry number, and marketable berry sugar content. So this led us into the supplemental light quality trials that we did. Ultimately, we selected Albion and Cabrillo as our two cultivars to move forward with. Albion because of pre-existing research and also giving it the benefit of the doubt due to the initial results that we got in the previous trial, and Cabrillo due to its high yielding and a relatively high sugar content as well. For this trial, we had 5 months of fruiting data. Light was controlled using Lassi, and this light was actually lower than the previous amount. We had 15 moles per meter squared per day with a maximum photo period of 20 hours. If we look over at defining marketable standards, we wanted US number 1 or better. So this really meant just finding about 10 grams or larger berries, diameter of greater than 1.9 centimeters, amount of red on the berry being greater than or equal to 90%, and no visual defects. So we were very restrictive on the berries that we did harvest from these treatments. We also used a general nutrition, just a 15, it was a 15, 5, 15 NPK, which breaks down to 15 to 12.5, a little bit of added iron at a nitrogen rate of 125 milligrams per liter. If we look at the experimental designs here, we can see we had our ambient trial, which used 2 micromoles per meter squared per second of incandescent night interruption lighting. These are day neutrals, and so they would be still flowering, but we just wanted to make sure that they were experiencing stimulated longer photoperiod. We had supplemental LED and supplemental HPS. The average DLI for the ambient light was 11.64 moles. For the LED is 15.37, and for the HPS it was 14.9. And so these were held together at a consistency, and this was allowed to fluctuate with the change in weather in the months and different conditions. Ultimately, the background spectrum of the light was this top image here, spectroradiometer output with the corresponding greenhouse. And for the LED and HPS, these individual printouts here would essentially just be overlaid on top of that background solar light. So jumping into the data, the first thing that I want to say is that all the data moving forward, unless otherwise stated, is looking exclusively at Albion. So the marketable fresh weight, the first thing that really stands out when we look over here at Albion, ambient, you can see that early on we have a very, very low yields, and then we continue to rise up until we hit May. It was about a 6.6 times increase from January to May. HPS, there was no significant difference. And LED, we had an initial flush with a drop off and then continued to rise after that. When we look down, and this is when we're comparing the individual treatments here, so ambient, HPS, and LED, we're comparing within a month. So for Albion, within a treatment, we're comparing each month to each other. The graph below that is comparing each cultivar or each treatment to one another within a month. So within January, how does ambient, HPS, and LED compare to one another? When we look down here, we can see that ultimately the ambient caught up with the HPS in terms of marketable fresh weight by March, and then also caught up to LED by May. So early on, we were getting very low yields in comparison. As the length longer and the total amount of light that those crops were getting increased, we see comparable yields, not significant yields. Ultimately, the greatest yields were achieved under LED, though. For the marketable fresh weight continuing, we're going to now look at the comparison of Albion and Cabrillo to one another and how they compare over all the months within a treatment. And we can see here is a very clear difference between the 2 different cultivars. We can see that our Albion was consistently outperformed by Cabrillo in all cases. And we can see that down here in the general numbers as well. We're also very picky about which fruit to obtain. And this is a much lower, even lower level of light than the previous study. So we know that there's ability to obtain higher yields. What we want to look at is the response within treatments, not necessarily the overall response. So we can see that it's almost doubling the amount of yield for Cabrillo as compared to Albion under both ambient and HPS. However, LED, they were more closely compared, but still about 57% greater yields. For the marketable berry number, this is the number of berries per square meter per harvest. Again, we can see this very similar trends, this increasing under the ambient conditions, on significance between months under HPS, and that same trend of increasing over time with the LED. This time, when we look at how the ambient compares to HPS and LED, we can see that it ultimately catches up to the HPS by April, but never catches up to LED, where the LED would have more berries per unit area. The marketable berry number comparing the two cultivars to one another, we can see that for LED and HPS, again, we see this significant difference where we have more marketable berries under Cabrillo than under Albion. But as we get into that lower level of light, consistently we see that even though there is a difference, it was not significant. And so the Cabrillo may just generally take off a lot more once it starts getting more light and more responsive to that. The marketable berry size, so this is our fresh weight in grams per individual berry. We can see that we have a significant difference between all months, so ambient, HPS, and LED. We have this increasing over time with ambient. We have an initial, higher yield of individual fruit for HPS, and then it stays pretty consistently steady. And then we have this decreasing over time associated with LED. And one of the reasons for that is we have this decrease of about 24% between January and May, is that the number of berries was significantly increasing over time for LED. And so we're getting more berries and less ability to provide the photostimulates to those berries for them to grow larger. So we're being sink limited in that case. Source to sink limitations. And that's also the case with the ambient light treatment, because when we have fewer berries on the plant, and as the year goes along and we're getting more light, then those individual berries, the fewer berries that are on these plants, are getting more individual photostimulates to them rather than being dispersed amongst a larger berry number. Marketable berry size, we can see again a significant difference between each of the treatments, the ambient, LED, and HPS. Under these, we have we can see that we have larger berries overall than the initial experiment did, and we have for Albion 16 for ambient, 16 for LED, and 14 grams for HPS. And for Cabrillo, we have larger, so about 16% greater under ambient, 12% larger under LED, and 8% larger under HPS. These are just some images that really help highlight the differences between both the cultivars as well as the individual treatments. So if we look at specifically at Albion, which is what we've been talking about consistently, we compare the ambient, HPS, and LED trials to one another. And this is just one harvest date on 5/3/19. And we can see the increasing yields across this. And then we compare down looking at Cabrillo, we can really see how much more yields we can obtain under with just simply based on cultivar selection. Here's some more images that really come to highlight that, the two cultivars in there. And it should say Albion got cut off. So you can see that under LED, we are starting to get much more greater yields for Albion, but still not nearly as much as Cabrillo. So now we can take a look at the Brix values. And again, we see this increasing over time for ambient early on in the season, where we have much lower irradiance values in the greenhouse, lower solar DLI. We have much lower Brix values, so down as low as around 6.5, reaching up to 8. Still not as high as the HPS and LED, which if you look at them, they're not significant, which is very good to see that if we maintain a consistent light, we can maintain a consistent quality over time, which is important. And ultimately, if we look down here at this graph, we can see that by May, as the days are longer, more light, there's no significant difference in fruit quality between all the different treatments for Albion. compare each to each other, you can see, just like before, the Albion has a higher Brix value than Cabrillo. So we get higher yields with Cabrillo, but the trade-off is a lower Brix. And that is the case across all the different treatments. So this is a slide that Neil showed. This one has a little bit more data points in it since that one. And really, what we did was we looked at 6 different light and 4 different CO2 concentrations. And ultimately, when you look at this graph, we can say the highest net photosynthesis, which is obtainable, is at the 2,000 micromoles per meter squared per second of PAR and 1,225 parts per million of CO2. However, that is not feasible, feasibly obtainable. And so if we look at the actual curve of the graph, as Neil had talked about, we can say that there's really diminishing returns above about 250 micromoles. So if we average out and assume a linear approach to this model here, we can say potentially at about 375 parts per million, or micromoles per meter squared per second of light, in combination with about 675 parts per million of CO2. So the jump here is the most significant. We have a much less significant jump from 675 to 950, as he had pointed out. And so we could say, okay, if we have assumed 375 micromoles over the course of a day, we could achieve something around, just over 25 moles per square meter per day of light. And this tells us that there is potential to keep, to increase not only the photosynthetic rate, but also the potential yields with source to sink relationships between the plant, which is what's going to move into the studies that we are doing. So ultimately, to summarize some of the stuff that I talked about, was that cultivars, Albion and Cabrillo, seem to hold the greatest promise for ones that are available in the US that we tested. The addition of supplemental light can significantly improve yield and fruit quality attributes. The supplemental light source itself also plays a significant role in the yield and fruit quality of these two cultivars. Even with the consistency in GLI, you can expect month-to-month trends within the cultivars, as strawberries tend to have flushes of fruit even though they are day neutrals. And the highest yields were under Cabrillo, but they did have the lowest Brix, so there was that trade-off. And lastly, we can expect that higher light, something greater than 17 moles, which was the first trial, and supplemental CO2 do hold potential for greater yields. And so, work in progress. Some of the stuff we're doing is obviously we're continuing replications with this, gathering more data to stack on top and continue to analyze the results. Additionally, we're looking at titratable acidity and phenolic analysis of these fruit and in response to these different treatments. And then upcoming research is the DLI and CO2 interactions on flowering and fruiting, as well as red, blue, and far red ratios on flowering and gene regulation associated with fruit flowering and development. With that, I will conclude my session of the talk, and I think we are going to open it up to questions.
Thank you so much, Jonathan. Thanks, Neil. Very interesting, great presentation. We do have 5 questions on the queue here, and then we can expand to a few more. So first question that I have here. Someone said that was unable to find an adverse effect from NOx, from NOx. Is there a paper about that? I think that came during Neil's presentation.
Yeah, hey, Erico. I'm kind of on speaker on my computer now. Can you still hear me okay?
Yes, we can. Thank you.
Great. So there's actually some nice work in the early 1980s from Dr. Mortensen, who is a researcher in Norway. And they found work with about a part per million of nitric oxide is where you would start to see some significant damage to the plant. We actually have a project at Cornell where we're looking at that under a broader range of concentrations with some of the newer commercial tomato varieties.
Perfect. Thanks, Neil. Second question. Must you supplement nutrients to match CO2 increases? So not only lighting, but nutrients as well?
Yeah, so the thought is the plant will be putting on more biomass, so it will also need to be taking up more nutrients. It is interesting, sometimes CO2 supplementation can cause nutrient deficiencies. What happens in that case is the stomates in the leaf do not have to open quite as much to get in carbon dioxide. So you don't have as much evapotranspiration, which is the driving force of uptake for like boron and calcium. So those are two in particular where there have been reported deficiencies with CO2 supplementation. So then things that one can do with airflow and dehumidification can also help drive uptake.
Perfect. So then the next one, should you not supplement with CO2 if conditions close the stomata? So the stomata aperture versus CO2 supplementation.
Right, so if there were like stressful conditions that would cause the stomates to close, like drought stress, like the irrigation didn't get turned on and the plants are getting closer to wilting, right, that would be a time when the plant's going to be not really receptive or not able to use the extra CO2 that you add. As well during the nighttime when the lights are off, right, the plant's not photosynthesizing, and that's not a time that we need to supply CO2. I do think it could be interesting to look at, if you remember, plants have different types of photosynthesis, and some of these succulent plants have a type of photosynthesis called CAM, where they absorb CO2, their stomates are open during the nighttime, and then they store it, and then they deplete those pools during the daytime when the lights are on. So maybe for like Phalaenopsis orchids, there could be a benefit of CO2 supplementation during the nighttime.
Perfect. So I have one more on the CO2, then I think we have a few questions for Jonathan. But we got this question show up 2 times about the sensor. So where would be the best place to allocate the CO2 sensor? So just to place the CO2 sensors to get some
Yes, that's right. So I'd like to see the CO2 sensors being placed near the middle of the plant canopy in a representative location. It's funny, actually, in a couple of our greenhouse sections at Cornell, they had installed CO2 sensors, and they're right on the end of the wall and not anywhere close to the plant canopy. So we've actually had to, we kind of use them as backup CO2 sensors to see what's, to check our sensors that we deploy more in the middle of the plant canopy.
Perfect, yeah. I think this question is for Jonathan. Jonathan, from your research, the question is, what was the red to blue ratio used?
It was a 90-10 using the Philips top light, and that had a uniformity value.
It's 95%.
Yeah, about 95% uniform light distribution at the crop canopy.
Okay, then related to that, someone was asking, why do you not use full sunlight spectrum LEDs? So why not a broad white LEDs? I guess that's the question. Any reason for that?
Yeah, it's so for the choice in the LEDs, it is what we had available to us at that time. So that's one of the big reason.
Okay, perfect. Recommended DLI for strawberry would be 17. So they want to check if 17 would be a good recommended DLI to grow strawberries.
So that's some of the research that we're actually starting right now, is looking at the higher DLIs on the fruiting development. Certainly 17 is an obtainable value and the plants can utilize it, but we assume that higher values are also beneficial. Just that question is, at what point do you start getting the significant diminishing returns? So I suspect it's higher than 17. Whether it's as high as a tomato plant in the mid-20s is up for debate. It's also going to depend on the individual cultivars that you're working with and the physiological characteristics of those plants, and the leaf area of each different cultivar is going to have an effect on their ability to capture the photons.
Sure. So I think we have one more for Jonathan, and then another one related to gases. So for Jonathan is, what was the plant density used in the strawberry trials?
It was 1 plant per square foot, so 10.73 plants per square meter.
Perfect. Very precise. Where is the question for Neil? I forgot. Oh, I found here. So the question is related to undesirable of gases. What are the general symptoms impacting plant health?
So ethylene is the one that I think we have more experience with as plant scientists. And with ethylene, so tomato is a very sensitive crop to ethylene, where even having 0.05 parts per million ethylene over like several hours a day, so kind of chronic low-level ethylene, what you get are the leaves bend downward. So the leaves almost look like they're wilting, but they're fully turgid. They're full of water. The plant has plenty of water, but the leaves were bending downward. And that would be called epinasty. Then typically at slightly higher ethylene levels, the flowers may abort and actually fall off of the plant. As well, you can get yellowing of the leaves or chlorosis of the leaves.
Great, thanks, Neil. Here is more like a comment, which is graphing diminishing returns using marginal returns would be more helpful for decisions. So that could be taken into consideration when showing the results. It's just, I think it's more a comment than a question, but would like to comment on that?
Yeah, just good feedback. Thank you.
Perfect. Yeah. One for tomato now. So we don't get any questions on tomatoes. Is there a difference between the amount of light moles per meter square for cherry tomato and a tomato on the vine?
Yeah, I would say I don't have enough information to answer that well. With tomatoes, we do think of them as being a high light crop. I am guessing there are some cultivar specific responses. This winter, we're actually going to be growing a cherry tomato variety in our trials, where in the past we had TOV varieties. So we will get a better handle on that this winter.
Perfect. Now a question about, I guess, the cultivation process. They were asking if there were any pollinators introduced into the experiment.
For the strawberries?
Sure.
Yeah. So no, in our case, the overall plant area was too small to use bumblebees, for example, for pollination. So what we do is we were using a leaf blower at low power, and every day go in and gently blow the canopy. It is certainly not the most efficient means of pollination. It is for a person's time, but in terms of the effectiveness of pollination, it is lower than if you were to use something like a plant, petal tickler, vibrator for those flowers, or to actually use pollinators that have the adequate control over the amount of time that they're allowed to pollinate. But if you're growing on a smaller scale, you just need to be very careful about using the pollinators and over-pollination of the fruit and causing abortion of that fruit.
Thanks, Jonathan. That's an interesting question here. When do you recommend to start the CO2 enrichment when you use HPS lamps? At the moment the lights come on, or just half an hour before the lights are on? So would you would you condition the greenhouse, or you start the CO2 supplementation at the same time as the lighting supplementation?
Yeah, my thought is it would probably not really be used until the lights are turned on. The plant needs stomates, and then we still need light as the driving energy for photosynthesis. But I'm not sure if there's other theories out there. I would have to look into the literature of trying to prime the leaf so it already has a high internal CO2 concentration when the lights turn on.
Also depend on airflow within the greenhouse, how much airflow you have to distribute that CO2 effectively, and how long that would take given the volume.
Right. If your CO2 has these polyethylene tubes to distribute it, and it's getting dispersed across the greenhouse relatively quickly, then it shouldn't matter. But if it takes a while from when you add CO2 to when it gets dispersed through the greenhouse, then you could consider doing that before the lights turn on.
Okay. Well, we're getting close. We're 7 minutes past the hour, and I don't want to take too long here. I think one general question that I had before we close the session, Jonathan and you, that's a question that we get all the time for indoor farmers, and could definitely be applied for greenhouse growers as well. But for the indoor growers, they ask if you need to pick one of those strawberries that you present today, Jonathan, considering the production costs, the yields from those specific species that you got, plus economic factors, which one would you recommend for an indoor facility, considering production costs and how much can you profit out of those, and how easy is to make, the marketing and the economics? So a very general question. Would that be possible to pick one or not really?
That's a very general question with a lot of it depends as part of it. I would say that given the cultivars that we worked with, which of course are limited, there are many cultivars out there, depending on where the grower is located, if they're in the US or if they're outside the US, that depends on what's available to them and the breeding programs. For what we trialed, given an indoor production facility, I would lean in the direction of, for example, Albion. And the reason why I say that, even though it has lower yields, it does have that higher fruit quality attributes. Now, not just Brix, there are aromatic compounds that are greater, higher degree of expression under the Albion cultivar than under Cabrillo. And so those value added components would become very important, particularly in a high financial, in the conditions of a vertical indoor production facility where your costs are much higher. So I would have to say Albion, but there is a lot of work that still needs to be done on the genetic availability to the average grower.
Great. I think, yeah, that's what they should be looking for. It's a very general question. I agree. So Jonathan, I just found, I was reading the questions from the Q&A window. I just closed that window and I saw that just through the chat, there is a whole bunch of other questions here, which we're not going to have time to answer. So what I would say, maybe I can follow up with both of you. We can see if we can provide short answers to these questions or just a few lines, and I can circle back. I can send you all the attendees by email. I can reply back. But I really would like to thank both of you for presenting on today's GLASE webinar. And would you like to make any final closing or any other comments before we go? And thank everyone else for attending the webinar.
Yeah, thank you. This has been great participation, and we really appreciate the questions and feedback. Have a good day, everyone.
Absolutely.
Thank you. Thanks, everyone, for attending. Thanks, Jonathan. Thanks, Neil. And I see you on the next webinar. Thanks, everyone. Have a good day. Bye-bye.
All right. Bye now.
Bye.